Welcome to Integrating with Partial Fractions. The pre-knowledge that you may find helpful is solving systems of equations using matrices and factoring polynomials. If you are not comfortable with using matrices to solve systems, including putting them into your calculator and using a calculator to solve those systems, if you're not comfortable with factoring polynomials of power higher than 2, quadratic, you may wish to watch those two videos first. They are in the folder regarding partial fractions. So, to continue, for those of you who are ready to go, here is the question. We have a function f of x equals a polynomial divided by another polynomial. And here are the restrictions. Thing one, p and q are polynomials. Thing two, the degree of p is less than the degree of q. And thing three, q of x can be written as linear factors. Hence the requirement to be able to factorize a polynomial. So let's look at a quick example, and then I'll go into what we're going to do. But the beginning of the example is the question, can you integrate the following function, x minus 13 over 2x squared minus 7x plus 3 with respect to x? And, it looks off the bat like a u substitution. We'll make u equal to, if you notice a little jumpiness in there, Google seems to be having trouble. They've signed me out a couple times right in the middle of making this video. So I will try to edit that chunk out, but there may be a jump. So u equals 2x squared minus 7x plus 3. Du equals 4x minus 7. And right off the bat, I can see u substitution does not work. So what we are going to do instead is we can take f of x, and since q of x can be written as linear factors, we're going to rewrite f as partial fractions. So here's all we need to be able to do. Thing one, we need to be able to factor q to know what goes on the bottom. Well, that's a pretty easy one because I've started us off with a quadratic. Q factors as 2x minus 1 and x minus 3. What goes on top? Haven't the foggiest. A and B. But what I do know is that to get back to the original function, I could multiply the first fraction by x minus 3, and I could multiply the second fraction, top and bottom of course, by 2x minus 1. They're now over a common denominator, which means that my numerator is ax minus 3a plus 2bx minus b over the quadratic. But I also know, looking back at my original problem, that this equals x minus 13 over that same quadratic. Doing a little highlighting, I noticed that I've got an, whoops, didn't mean to do that. I meant to. There we go. I've got, why is it not highlighting? ax plus 2bx equals 1x, a plus 2b equals 1. And I've got negative 3a minus b equals negative 13. I've got a system of two variables, two equations, which I can easily solve using a variety of strategies. And what I discover is that a is equal to 5 and b is equal to negative 2, which now allows me to rewrite my function f of x as 5 over 2x minus 1 plus negative 2 over x minus 3, which means that if I want to integrate f of x, I get 5/2 the natural log of absolute 2x minus 1 minus 2 times the natural log of x minus 3 plus a constant. So let's recap. F of x equals p of x over q of x. P of x and q of x are both polynomials. P has a degree that is less than q. Q can be factored into linear factors, and therefore f of x can be written as a over q1 of x plus b over q2 of x plus ... as many as I need. And the integral of each of these factors, because they are linear factors, q sub I is a linear factor of q. Every single one of these integrals is going to be a natural log, and I will have a string of them that I can then do what I need to do with. Okay, that is the method of partial fractions. Please remember the restrictions on this method. When do I use this method? I use this method when these three things are true of my function. And that is it. All right. Thanks for watching. Hope you learned something.